Okay, so constant velocity, object changes its position by the same amount every second. But on this graph, in the first 2 seconds, the object only goes this far here. Okay, in the next second, or next 2 seconds, sorry, it goes this far. Okay, and the next 2 seconds after that, that far. Okay, next 2 seconds after that, further. Okay, next 2 seconds after that, even further. Okay, we can't go another 2 seconds because that pattern ends right here. Okay, you can see that the amount it travels is increasing each time. Okay, so instead of going 2 meters every second, now it's going a little bit further every second. Well, the only way to go a little bit further in the same amount of time is to go faster. Okay, so when I see a curved line, okay, I can see that y's rate of change is changing. Okay, and that's on any graph. Okay, if I see that there's a curve on any graph, I know that y's changing at a different rate all the time. Okay, on this graph, that means the rate of change of position is changing. That's acceleration. The only way for that to happen is for the object to be going faster. Okay, everybody with me there? All right. So in this part, the object is accelerating. What's it doing here, between here and here, let's say? So I'll move that line out of the way. Yeah, it's accelerating backwards during that part because the line stops getting steeper and starts getting flatter. Okay, if I had a horizontal line on a position time graph like this, what's that object doing? Nothing. Its position isn't changing. Okay, a horizontal line on any graph means y isn't changing. The object isn't doing anything. Whatever that graph is showing, it's not doing that. Okay, it's just sitting there. Everybody follow me? Okay, or whatever's on the y isn't changing. Doesn't mean it's sitting still. Could mean something else. It's just y is not changing. All right. So in part B, we see that the curve is getting flatter, and then after the top, what is it doing? Is it still a curve? Still a curve, right? So is it accelerating again? Okay, accelerating backwards. Yeah. Okay, and then in part C, so from here to here, that line is getting flatter again. Do you agree? Okay, so during part C, the object's slowing down and actually coming to a stop. Okay. What do you suppose this is a graph of? Throwing something up in the air. Okay? During this first part, that's me accelerating the marker. Okay? I'm making it go faster and faster and faster during that part. But as soon as it leaves my hand, I'm not pushing on it anymore. What's acting on it now? Gravity. And what's gravity doing to it? Pulling it downwards, exactly. Okay? It's accelerating it downwards, in fact. At what rate? 9.81 meters per second squared. So as soon as it leaves my hand, it's accelerating downwards at 9.81 meters per second squared. So it goes slower and slower and slower, and then right at its maximum height, what does it do for just an instant? It stops. And then it accelerates downwards. Well, it was accelerating downwards the whole time, but now it actually starts to move downwards. Okay? It's possible for the acceleration and the displacement to be in opposite directions. Okay? It was accelerating downwards while it was moving upwards. That's okay. Okay? That can happen. right? So it gets to the top and then it accelerates back down at the same rate it was accelerating before. And when it gets to my hand, I catch it and bring it to a stop. Okay, now, I would never put a graph with some weird shape on your exam and go, hey, what's happening? What's this a graph of? It's not really a fair question. Okay? But what I could ask you, and this would be fair, is what's the object doing in part A? What is the object doing in part B? That would be fair. That requires you to analyze the graph and figure out what's going on. Okay? But to say, what is this a graph of? Well, that graph could also be of me running into a bungee cord. Okay, or having a bungee cord tied to me, okay, that's slack, and I just run away from it, and then when it starts to take up, okay, what would it do to me? It would slow me down, right? I would start to accelerate backwards, so I would slow down, get as far as I could before being shot back the other direction at the same rate. Okay, that could be a graph of that instead. Okay, it's showing an object that's being accelerated one direction and then being accelerated another direction and then moving in that direction after. Okay. All right. Now, according to our lab and what we did on Monday, okay, this number, the slope, on a position versus time graph represents what? Not on a position time graph, on a velocity time graph, yes? Velocity. Okay, let's review why. Okay, just as a quick review here. So on this graph, or even on this graph, okay, y is a position value. Agreed? This position is on the y-axis. Okay, so in this case, y would be up there, or it could be here, or it could be here. It could be anywhere but here. Okay, so it would be a y value somewhere. In other words, it would be the final position of the object. That would make b the, okay, maybe let's review what b is here. On this graph, that's b. B is the y-intercept. It tells me the value of y, in this case position, at time 0. What do we call the position at the beginning of something? The initial position. Okay, so the initial position is b. Okay, what is x? What's on the x-axis? Seconds, which measure time. Sorry, time equals x. Okay, so I've got initial position, final position, and time, and I've got one more letter in that equation, m. Well, the only formula I have that has pi, pf, and t in it is this one. Okay, so that means then that m, if I manipulated for m, I would have 1.5 equals y minus 0.25 over x. Well, isn't this that? So when I calculate the slope on that graph, I'm calculating the rate at which position changes. The rate of change of position is velocity in meters per second. Okay, again, I don't memorize that the slope of a position versus time graph is velocity. I could, it always is, okay? But it's better for me to be able to look at this graph and go, okay, what's on this graph? What are the possible values for y and b and x and m, and figure it out. Okay, that skill I can apply to any graph. Okay, and we're going to apply it to a new graph here in just a minute. Okay. Now, one other thing, you won't be actually asked to do this, but it's important that you know about it. okay? What if, so in part A, the object we've said is accelerating, right? It's going faster. What if I wanted to know exactly how fast the object is going at 10 seconds? Could I calculate that? Okay, I can, but probably not in the way you're thinking. Okay, a lot of people just say, oh yeah, you can calculate velocity, you just do this. Average velocity equals displacement divided by time. Okay, well, I'm asking you about a single point. Okay, so should I just like do this and say 6 divided by 10? That'll calculate the average velocity between 0 and 10 seconds. That looks like this. Come on, do what I want. Being so finicky, come on. Stop doing that, damn it. Okay, fine, you can play that game. Okay, does that line represent how fast the object is going there? No, that line represents the average velocity between 0 and 10 seconds. By the time it gets to 10 seconds, it's accelerating. It's going faster than that already. Okay? So, quick review of one thing. The slope of a line on a velocity time graph represents, the slope of a line on a position versus time graph represents velocity. Okay, I'm about to teach you the only thing I understood in university calculus. To a mathematician, a curve is an infinitely large number of infinitely tiny straight lines, and they constantly get steeper or shallower depending on the curve. Okay, so when a mathematician looks at this curve, they see it like you see a low resolution video on YouTube. Okay, so you got like a really slow connection on your phone, you're trying to watch this video on YouTube or TikTok or whatever you guys watch these days. Okay, and because your connection's really bad, it runs it at low resolution. What can you see? They look square. Pixels. You can see the pixels. Okay, so to a mathematician, they look at this line and they see the individual lines that make up that curve, like you would see pixels in a low resolution video. Okay? So what that means then is that at that very point, there is an infinitely small straight line. And if I can calculate the slope of that infinitely small straight line, I'll know how fast the object is going right there. The problem with that is that line is infinitely small. I don't know what its y-intercept is. I don't know what b is or any of that because it's this small. It doesn't have a b. I don't know where it goes. It's this big. Okay? So what they do is they say, that's fine because we can use math, unfortunately. Okay? We can draw a line like this. What do we call a line that touches a curve but doesn't cross it? Starts with T.
Tangent.
It's tangent. Okay, you guys heard that term before? Okay. A tangent is a line that touches a curve but doesn't cross it. That means that that line I just drew is parallel to the curve at that spot. If those lines are parallel, do they have the same slope? Could I calculate the slope of that line? It's long enough, right? Now that line's long enough, I can do that. Okay? I couldn't do that with the infinitely small line, so I cheat. And I draw a line that's parallel to it that's long enough to calculate the slope. Okay? Now, here's the reason why you're never going to be asked to do this. If I give everybody this graph and ask them to calculate the instantaneous velocity at 10 seconds, everybody draws a tangent line.
and everybody's tangent line is different. And then I have to say, okay, I'll accept slopes between 2.5 meters per second and 2.65 meters per second. And anything outside of that is wrong. So you do this really well, you draw a tangent line that you think is right, and you get 2.66. Is that fair? That's why I don't do it anymore. Okay. It ended up that I had such a big range of things that were acceptable that basically everybody got the question right. There was no point to it anymore. Okay, so as long as you understand that a curve is an infinitely large number of infinitely small straight lines and that they all have a slope, that's what I'm looking for. Okay, can we agree we're all good with that now? All right, let's look at velocity versus time graphs. So a position versus time graph tells us where the object is at various points in time. A velocity time graph shows us how fast and in what direction the object is going at various points in time, because time is still on the x-axis. Okay, so where a position versus time graph told us where the object was, velocity versus time graph tells us how fast it's going and where it's headed at any point in time. Okay, so that means I can read different things off of that graph. I can also calculate some things off of that graph that I couldn't off the position versus time graph. Okay? And in fact, it's possible for those graphs to be showing me the same thing. If they're showing me the same thing, are they going to look alike? The answer is no. It's from two different points of view. Okay? If you like Star Wars, it's like Vader is your father. Vader betrayed and murdered your father. It's the same story from two different points of view. They're both true, but they look a lot different. Okay? So, let's have a look at these two graphs. Graph on the left is a position versus time graph. Okay? What is this object doing? Okay, this is where our analysis skills, our analytical skills come into play. Okay, this is a position time graph. Okay, and according to this graph, every 2 seconds, the object goes the same distance. So this is an object traveling at a constant velocity in a forward direction. Okay, that's the analytical skills I want you guys to have. Okay, so this is showing an object traveling at a constant velocity in a forward direction. Okay, could I calculate the velocity of this object? Pretty sure I could. Okay, like I could even do this. Okay, because I can get all of these numbers, and I know that on this graph, m would be the rate at which I change my position. That's velocity. So I can calculate velocity off of this graph. Again, I didn't memorize that. I figured it out. Okay, so I'm going to go, all right, here's my final position. That's y. Here's my initial position. That's b. And here's my time. That's x. Okay, so now I've got all the numbers except for m. So I'm going to calculate m. Okay, that's going to be y minus b over x, which is final position minus initial position divided by time. So I'm calculating velocity here. Okay, so velocity is going to equal 1,400 meters, positive 1,400 meters. Okay, that's where that is, minus positive 100 meters, because that's where b is. Okay, divided by 5 seconds. Okay, so v is going to be 1,300 meters, positive 1,300 meters, divided by 5, 260 meters per second in a positive direction, according to that graph. Okay, everybody okay with what I did? Did I have to use the y equals mx plus b, or could I have gone straight to final position minus initial position divided by time? Could have done it either way. Would have got the same answer. Okay, the graph on the right is a velocity versus time graph. What is it showing? Same thing. How many people's gut reaction was the object's not moving? It's okay, you don't have to admit it. Okay? But it's a velocity versus time graph with a horizontal line. Horizontal lines always mean y isn't changing. On a position time graph, that means the object's not moving because its position isn't changing. But on a velocity versus time graph, a horizontal line means the velocity isn't changing. Okay? That means it's traveling at a constant velocity, unless the line is going along the x-axis. In which case it would also mean it's not moving because its velocity would be 0. Okay? But in this case, that line looks to me to be right about where 260 meters per second would be. Agreed? Okay. So those two graphs are showing the same thing, but it looks a lot different. Okay? Because it's two different points of view. Where the object is versus how fast it's going. Okay? Very different points of view. Okay, could I calculate the displacement on this graph? On the position time graph? What's the formula for displacement? You guys are getting shy on me. Displacement is final position minus, right, okay? I actually already did that up here, didn't I? Okay, I needed the displacement to get the velocity. From a position versus time graph, you can always get the displacement because final position minus initial position is how you get displacement. Okay, I can always get it from that graph. Right? In this case, that's going to be 1,400 meters minus 100 meters. So the displacement is 1,300 meters in a forward direction. Everybody okay with what I did there? All right. Can I calculate the displacement with the other graph? How would I do it? Yep, multiply meters per second by time. Okay, here's what I think, I'm not going to speak for Levi, but I think this is what he was thinking. Okay, he saw on this graph that he had velocity and that he had time. And I asked for displacement. Well, in this formula here, I can get displacement if I have v and t. So if I manipulate this and go t times v, remembering that this is average velocity, okay, I can get d. Well, the time is 5 seconds. Okay? The average velocity is 260 meters per second. Right? It's moving at that velocity constantly. So if I multiply 260 by 5, that's pretty much the opposite of what I did right there, isn't it? I better get 1,300. Okay. All right. When I did that, did I kind of calculate the area of this rectangle? I went base times height, right? 5 seconds times 260 meters per second. Okay, gave me the area of that triangle, which just happened to, or sorry, that rectangle, which just happened to be, okay, the displacement, 1,300 meters of that object. Okay, I'm going to erase all my scribbles here. I'm going to bring this handy little line back down here. What's that object doing?
Accelerating.
Yep. Faster or slower?
Faster.
Faster. Okay? It is accelerating in a positive direction. Its velocity is increasing in a positive direction. I would accept any of those as an answer, by the way, on, let's say, a quiz or a multiple choice item on a unit exam. Okay, that's a prime multiple choice question right there. I throw a graph up there and I say, what is this object doing? A, accelerating in a positive direction. B, traveling at a constant speed. C, it stopped. D, impossible to tell. By the way, impossible to tell is like never the right answer if that's ever an option. Yeah. Okay, easy enough question? Okay, but it requires you to analyze that graph. It requires you to look at it and go, all right, velocity is here, the line's going up, so velocity is getting bigger. Okay, that's happening over time. Any change in velocity over time is acceleration. Right? We learned about that formula last week. Okay, this is where that formula comes from. Okay. Now, that formula there is kind of very similar in form to this formula. Would you agree? Right? In form, their shape is very much the same. This was the slope of that line, agreed? So, could this be the slope of that line? Right? That graph is showing me that acceleration is velocity is increasing from 100 to 400 meters per second over a 5-second interval. Okay? I should be able to calculate the rate at which velocity changes by finding the slope of that line. Okay? Again, that's where that formula comes from. Okay? So if we were going to do that, right, we would say, okay, the final velocity would be 400 meters per second. The initial velocity would be 100 meters per second. And our time would be 5 seconds. Okay, well, so that'd be 300 over 5 should be 60 meters per second squared. Positive, I think. I'm doing mental math, but I've been pretty good today at my mental math. Everyone okay with that one? All right. Do I have to memorize that the slope of a line on a velocity versus time graph is acceleration? I can, but I'd much rather do what I did, which was apply the same skill I had on the position time graph to the velocity time graph, or whatever time graph. Okay, doesn't matter. I can apply that skill to any graph. Okay, another question for you. When we were looking at the rectangle, okay, we said the area of that rectangle represented the displacement. Could the same be true for the angled line? Okay, it absolutely can. It absolutely is. Okay, because what we did when we calculated the displacement here, is we did average velocity times time. The average velocity was 260 meters per second, and the time was 5 seconds. Now, it was fairly easy because the velocity was constant. We knew what v was. How do I get the average velocity for an angled line where the velocity is changing? Okay, let me ask you a different way. How do you calculate the area of a triangle?
Base times height divided by 2.
Base times height divided by 2. Okay, the base is time, agreed? The height is velocity. If I divide my final velocity by 2, would that number represent my average velocity during that time? Absolutely would, because I'm accelerating from this velocity to this velocity, okay, uniformly from here to here. So for half of this, I'm going slower than that number. For half of this, I'm going faster than that number. That's absolutely my average velocity, okay? And that's why
going base times height divided by 2 is exactly doing this, time times average velocity. Okay? Still perfectly valid to do it that way. Okay? Everybody okay with that? Okay, so there's a little cheat here, okay? I mean, I don't want you to memorize things, but if you're having trouble with the analytical part, okay, this rule works. The area between the line and the x-axis on this type of graph represents displacement. Now, it may be a lot of shapes. You might have to calculate the area of a lot of shapes, but it would work. Okay, now, does the area under the line always represent something? Like on any graph? Answer to that's no. On some graphs, the area under the line is completely meaningless. Okay? For example, on a position versus time graph, okay? If I take the height of this and divide it by 2 and then multiply it by this, I'm still just multiplying meters by seconds. I have no idea what meter seconds measures. Okay? Sometimes the area is completely meaningless. Okay? On the velocity time graph, it does calculate displacement because of what you're doing when you calculate it. You're taking average velocity and multiplying by time. On this graph, I'm taking average position and multiplying by time. That doesn't mean anything. Okay. Okay. So this is a graph of a runner. What's the runner doing in this part of the graph?
Accelerating.
They're accelerating, okay, from 0 to 8 meters per second. What are they doing in that part of the graph? Running at 8 meters per second. Okay, and then what are they doing here? Slowing down, and they actually stop, because that line goes down to 0. At the end of that, their velocity is 0, so they do stop at the end. And that's what you do in a race, right? You run until you're running as fast as you can, and then you run as fast as you can, and then you cross the finish line and you stop. Okay, that's a perfect example of what a racing graph would in fact look like. Okay, let's try something here. Let's assume that this isn't curved at all, okay? And that that's perfectly straight and that this doesn't curve at all. I've got a triangle, a rectangle, and a triangle, okay? Calculate for me how long this race is in meters. And I want the displacement of the runner. Okay, so we said a minute ago that if I find the average velocity and multiply it by time, I'll get the displacement. Everybody okay with that? Right? We're just saying average velocity times time equals displacement. Okay? Can I get the average velocity of this object between 0 and 5 seconds? I can, because it accelerates from 0 to 8. So the average would be half that. 4, right? Because if I want to calculate the area of this triangle, I would take the base, 5 seconds, and multiply it by the height, 8, divided by 2. Base times height divided by 2. Okay, so I'm going to have 8 divided by 2 times 5. So 4 times 5. Okay, that part of the race is 20 meters. This part of the race is easy. Travels at a constant velocity of 8 meters per second for 5 seconds. How far does it go? 40, right? 8 times 5 is 40. Okay, now, oh, sorry guys, I forgot to say, did everyone make that 14 or did they make it 15? Or maybe you guys were stuck on that one. Okay, so this line appears to stop before 15 seconds, agreed? I'm going to say it ends at 14 seconds, just going to estimate. Okay, so the height of this triangle is still 8, but it's a triangle. 8 divided by 2 is 4. So average velocity during this part is 4 meters per second, okay? And then multiply that by 4 seconds. All right, so in this part, he goes 16 meters. That makes sense. That triangle's a little smaller than that one. Okay, so how long is this? How far did he run? 20 plus 40 plus 16.
Okay? Now, you could also argue that the race was actually only 60 meters. Why?
Because you would slow down after you finish.
You would slow down after the finish line. That's a multiple choice question right there. Okay, and that's seeing who's on the ball. Okay, because 60 meters would be the length of the race. 76 meters would be their total distance traveled. Okay, is that a dirty trick question? Absolutely. Okay, I'm not above that, just so you know. Okay. All right, I got a velocity versus time graph. What's this object doing? Moving at a constant velocity of 5 meters per second in a forward direction. Okay, I see that there's no negatives on this graph, so I'm going to assume it's forward. Okay, what's the acceleration of this object? 0. If you're traveling at a constant velocity, are you accelerating? Okay. Also, where can I find that number?
In the equation.
Right? The slope of this line is 0. The slope of this line would tell me the rate at which velocity is changing. And the velocity is not changing in this graph. Okay, you follow my analysis there? Right? I'm looking at what's on this graph, its velocity. Velocity is not changing. The only thing I need to memorize is the definition of acceleration. Acceleration is the rate at which you change your velocity. Well, velocity is not changing, so there's no acceleration here. All right, could I very quickly calculate the displacement of this object? What's the displacement of this object? 50 meters. Okay, now if you're looking at this and going, oh crap, and your eyes are the size of dinner plates right now, don't worry. Okay, all we did here was just do a little bit of analysis. We already said the object was traveling at 5 meters per second. The graph goes to 10 seconds. If I go 5 meters per second for 10 seconds, I'm going to go 50 meters. Okay, I don't even have to write out v equals d over t and do all the manipulation or anything. I just have to use analytical skills. Okay, and then I can do that math. I can do 5 times 10 in my head. Okay, and I'm not very good at math, so I'm confident that you guys can all do that too. Okay. All right. What's the acceleration of this object?
2.96.
2.96 meters per second squared forward, or positive. Okay, how do we know that? It's in the equation. Okay, this is a graph clearly showing an object whose velocity is changing over time. There's clearly an acceleration going on here. Okay, and because I can look at this graph and say, oh, the slope would represent how quickly the velocity is changing, I don't need to do any math. I can just look at that equation and go, it was nice, awfully nice of Google to spit that number out for me. Okay? And save me having to figure out what VF is. And I already know, what's the initial velocity of this object? Negative 0.182. Remember, B is your y-intercept. It is the value of y at time 0. This line ducks just a hair under 0. Okay, that means the object was actually traveling a little tiny bit backwards when it started to go forwards. Okay, everybody all right with that? Okay. I'm going to put 2 things up on the board. I want you guys to calculate them for me. Okay, using this graph. Okay. I want you to calculate those two things for me. Okay, you have the equation for the line, and that might be helpful. See if we can transfer our skills from position time graphs to velocity time graphs. I'll be right back. Okay, you got it figured out? How many people think they got it? Okay, so, oh shoot, I was recording the whole time. No. Okay, so on this one here, we've got y on the x, or on the, we've got y on the x-axis. We've got velocity on the y-axis. We've got time on the x-axis. Okay, so if it asks me how fast, am I solving for an x value or a y value? I'm solving for a y value. Okay, y on this graph, even if it's not on this graph, it's beyond this graph, is final velocity. Because initial velocity is always this number. So if I'm wanting to solve A, how fast will it be going after 34 seconds, they gave me x. They told me the acceleration, and this is VI. Okay, so all I have to do is go y equals 2.96 times 34 seconds, okay, plus
negative 0.182. And I will have my final velocity. So 2.9696 times 34. There we go, times 34, okay, plus negative 0.182. All right, so after 34 seconds, this thing will be going 100.5 meters per second forward. Everybody okay with what I did there? Okay, when it comes right down to it, we know that m equals y minus b over x. Okay, well, that's the same as saying this, vf minus vi over t. If I wanted to solve for vf, which is essentially what I did here, I would go a times t plus vi. Well, a times t plus vi. That's what I did there. Just a manipulation of the acceleration formula because I had all those numbers on the graph. Okay. All right, so part B. How long will it take? What am I solving for? Time, which is on which axis? All right, so I'm solving for x. They told me a velocity. That means they told me y. Okay, so I'm going to take y equals m times x plus b, and I'm going to solve for x. So I'm going to subtract b from both sides and then divide by m. Effectively, I'm going vf minus vi over a to get t. Essentially what I'm doing here. Okay, so I'm going to have 130 minus negative 0.182 divided by 2.96. Okay, just using my graphing equation, right? 130 plus 0.182 divided by 2.96. Why does it keep putting a 3 when I want a 6? All right. Oh, I missed a decimal. Okay, this number. Sorry, guys. I was like, whoa, that number seems really small. And divided by 2.96. Better. Okay, so it'll take 44 seconds. Okay, to do that. Did I do anything different than what we learned how to do on the position time graphs? Okay, this is one of those analytical skills. You can apply it to any graph. If you can use y equals mx plus b, you can use it on any linear graph. Okay, and that's all we did to do that. Questions on what we did there? Okay. Is this object accelerating? At what rate? 3.3 meters per second squared forward. Okay, I want you to calculate the total displacement here. But we're going to do it together because this is a little bit different. What shape do I have here? I have two shapes. I have a rectangle under a triangle here. Right? This line doesn't go through the origin. That means I don't have a single triangle or a single rectangle. I have both of those things. Okay? What this ends up looking like is this. This rectangle whoa, I got really wiggly there. Okay, with that triangle on top of it. Can I calculate the area of both of those? Okay, and remembering that, of course, the area is taking the average velocity and multiplying by the time. So what's the average velocity I'm going to use for the blue rectangle? What's the height of the rectangle? Sorry, I should finish drawing the rectangle. What's the height of that rectangle? 4.14 meters per second, right? It stops at the y-intercept.
Okay, basically that rectangle is saying, here's how far the object would go if it didn't accelerate. And what we're gonna do is then add the triangle on, which is how far it traveled while accelerating. Okay, and then we put the two together and we'll get the total displacement of the object. All right, so for here, okay, the displacement is gonna be average velocity times time. In other words, base times height, because it's a rectangle. Right? And so that's gonna be 4.14 times 10, so 41.4 meters for the rectangle. All right, now to calculate the area of a triangle, I need the base, 10 seconds, I'm good there, okay? And I need the height of the triangle. I don't have that, do I? And I don't know where exactly this line is at 10 seconds. Could I calculate the height of that line at 10 seconds? Using? Would the height of that triangle be its y value at 10 seconds? Okay. So what I'm going to do here then is go, all right, y equals 3.3 times 10 plus 4.14. Well, okay, that's fine. That's going to be 37.14. Okay, but here's the thing. That's the height from here to here. I only want from here to there. Would you agree? Triangle doesn't go all the way to the x-axis. So how high is the triangle? 33, yeah. This is 37.14. This is 4.14, okay? The height of the triangle is 33 meters per second. Okay, and that might sound weird. I said the height of the triangle is 33 meters per second, but it is. This is a velocity time graph, right? We're not actually doing the height of the triangle. We're doing the change in velocity. Okay, so can I calculate the area of that triangle now? Right? So average velocity times time equals distance. That's going to be the height over 2 times the base. Okay, so 33 over 2 times 10. So 16.5, 165. Okay, so the triangle's 165 meters. The rectangle underneath is 41.4 meters. Add those together, total displacement's 206.14. I think my mental math is okay there. Okay. Now, did I have to do any like wickedly hard math? I did grade 7 geometry. Okay, literally, that's what I did. But I had to know what that geometry represented. Okay, people get confused, like I'm calculating the area of a triangle. No, the area of the triangle represents something. That's what you're calculating. That's what the analytical graphing skills get you. It's like, oh, if I want displacement, I need average velocity and time. I can get it in this way. That's what we want to be able to do. Rather than memorize. Always calculate the area under the triangle. Guys, when people memorize that, they do it on everything. Do you always want to do that? The area under the line doesn't always represent displacement. If it's on a position time graph, it's meaningless. Okay, so we have to remember which graph do I do this for? What does this graph represent? What am I seeing here? Okay. All right, I'm going to give you guys, let's say, a 3-minute break, okay, here in the classroom, and then we're going to talk about this graph. All right, what's this object doing? Okay. Okay, let me ask you this instead. What's the initial velocity of this object?
27.
27.5 meters per second, right? At time 0, right, this is my y-intercept way up here. It's just because it's backwards, right? Okay, so my y-intercept's way up here. It's positive 27.5 meters per second. By the end of this graph, what's my final velocity? Where does the line go? Don't be afraid to say it. You're looking at it and you know it. This thing comes to a stop, right? That line goes down to 0 and doesn't go through it. That means that at about 9 seconds, okay, that object comes to a stop, according to the line anyway. Okay. So my initial velocity is positive 27.5. My final velocity is 0. What's my acceleration?
Negative 3.2.
Negative 3.02 meters per second squared. If something's acceleration is negative, okay, does that mean it's moving backwards? This object moving forwards. Okay, think about this. Here's where the analysis comes in again. Are there any negative numbers on this? Then every velocity of this object on this graph is positive. That means this object is moving forwards for the entire duration of this graph. After 9 seconds, it won't be. Okay? If it continues to do this, it'll go down into the negatives. But on this graph, the object is always moving forwards. Does that seem weird? Its acceleration is negative. How can it be going forwards if it's accelerating backwards? The answer is that's exactly how you slow down. Okay? You slow down by accelerating in the other direction. This is something that, as North Americans, we struggle with because we're so tied to automobiles. Okay? When you push the brake, do you slow down? Does the brake ever cause you to go backwards? That's exactly why we're stuck on that as North Americans. Okay? We always see negative acceleration as something that stops you. In real physics, negative acceleration continues past the stop. Okay? So imagine, I keep going back to this example, but let's say I strung a bungee cord across here. Right? I'm running forwards. I hit that bungee cord. I'm still going forwards, but I'm accelerating backwards. I'm slowing down. I'm slowing down. Eventually, I'll stretch that bungee cord as far as I can before I, for an instant, stop. And then start to go in the direction I was accelerating. It's possible to move in a direction opposite your acceleration. It just means that your velocity is going to decrease, okay? Or become more negative. That means go from 27.5 to 0. Everybody okay with that idea? Okay? It's tricky sometimes. The first time we talk about it, it's like, oh, you can't accelerate backwards, but move forwards. Well, it happens every time you throw something in the air. Right? We talked about that earlier today too. If you throw something up in the air, as soon as it leaves your hand, it's accelerating downwards. It's still moving up, but it's accelerating down. That's why it comes back. That's why we have that rule. What goes up must come down, because that's how that works.
What if, like, moving forward with the bungee cord without a bungee cord snaps?
Then my graph would change. Okay, so my graph would look like this, and then all of a sudden the points would go like this. Right? Then it wouldn't be a linear function. It would be two different functions. Right? There'd be that I slowed down, but I powered through it, and I snapped that cord, and I just kept then I would do this again. Right? I would start going the other way. So I'd start accelerating the other way. I'm always going that way. Okay? Everybody all right with that? Those are, again, analysis questions. I have put a question just like that as a multiple choice question and asked exactly what I asked you. Okay? What direction is this object going? A, forward. B, backward. C, it's not moving. D, impossible to tell. Remember, it's never impossible to tell. You can always tell. Okay? And I get people on that one because they see the line going down. As soon as we see something declining, we automatically think negative, okay? And they pick backwards, even though none of the values are negative. Okay? Does that make sense? Okay, that's just look at a graph more carefully than just, I glanced at it and I saw this and now I'm done with the graph. Okay, it's gotta be more than that. It's gotta be, okay, I'm gonna look at the numbers on the graph, I'm gonna see the patterns on the graph, I'm gonna work those things together. That's analyzing a graph. Okay? All right. I want you guys to calculate a couple things using this graph. I want you to calculate for me the velocity after 22 seconds. And the displacement of the object to 9 seconds. Okay, this is 9 seconds right here. Right, I'll give you a few minutes on